Hello everyone. I welcome all of you for CAENexus basic training. We thank you all our users to partner with Nexus and automate their CAE workflows using CAENexus. These sessions are mainly focused on authoring abstract models. The training comprises three sessions. The first session will cover overview of CAE workflow. The second session will give the details of abstract model authoring, and the third session will help to understand productivity improvement tools in CAENexus. Before starting actual session, let's see some key points here. Firstly, this training session is focused for CAE analysts. So this is not a solver training, rather it is a prerequisite. Please remember that CAENexus is a knowledge capture and workflow automation tool. So extra efforts are required to automate the workflow, which will helps in improve production work. But we need to appreciate that authoring abstract model is a one-time job, and it is going to save a lot of analyst time, and it will help improve production work. At the end, CAE workflow automation is a team effort which will help in order to get best results for organization. So let's start with our first session. This is the agenda for first session. First, we will see what is CAENexus, then what is CAE geometry, abstract model authoring, and we will know how CAENexus work or CAENexus workflow. So, what is CAENexus? CAENexus is a novel CAE preprocessor based on unique abstract model technology intended to automate CAE workflows. Automation of CAE workflow is a central idea and concept behind the product CAENexus. Analysis domain is divided into three subdomains. The first one is pre-processing, second one is processing, and third one is post-processing. So CAENexus is a preprocessor based on abstract modeling technology. Also, CAENexus report framework generates automatic simulation report. So CAENexus falls in pre and post processing subdomains of analysis. CAENexus supports all CAD and CFD solvers. CAD modeler supported are Creo, SpaceClaim, UG, and SolidWorks. The CFD solvers supported are Accusol, Fluent, StarCCM Plus, and OpenFOAM. Let's start with real geometry, which is easy to visualize and understand topologically. Let's start with simplest geometry like a cube. Here, tube is defined by topological connection of 6 faces, 12 edges, and 8 vertices, and an interior region. Similarly, a surface of cube can be topologically defined as 4 edges, 4 vertices, and a face. Also note that this face has two sides. One is directing towards the volume and second one is directing towards void. So please remember that a 3D computational domain is defined by topological connection of faces, edges, and vertices in a hierarchical order. For practical purposes, we need to create a non-manifold computational domain for meshing with multiple volumes in a region. So let's understand what is non-manifold CAE geometry. You can see here two cube structures touching each other representing volume 1 and volume 2. Now a CAD model will have two surfaces of each volume. At the interface, one belonging to each volume. But a non-manifold model will have only one common surface belonging to two volumes. We can call it as a relation between two cubes and defined by a common face. Similarly, one can define a relation between face and outside, that is wide, uniquely. So please remember that in a computational domain, relations can be defined between different geometric entities. Like a cube, all practical CAE geometries, no matter how complex they are, can be represented by topological connectivity of volumes, surfaces, curves, and points. We can physically visualize the geometry and hence it is easy to understand. This geometry is to what we start with setting up CA simulations in traditional approach. Let's now move towards main objective of this session is to understand abstract model authoring. Like we define real geometry using topology, we can also define abstract geometry, which is just imagining imaginary, not real one. So what is abstract? Abstract is something that exists in thought or as an idea but not having a physical or concrete existence. Let's take an example. When we say color, it does not let us visualize which color. But when we say blue, it immediately gives some meaning and we can visualize a concrete information. Let's now think about CAE simulation. A term fluid is an abstract term which does not give a concrete visual, while a pipe can be visualized easily. The terms fluid and solid represent some kind of three-dimensional object but without any shape. Although they do have some physical significance, that is material type in CAE simulation and important for analysts. The terms pipe and bolt have definite shape and three-dimensional. Also, they represent a concrete existence in some real product and are important for designer. We can define various abstract classes like fluid, solid, size, etc., which can be used to define simulation physics independent of geometry. With traditional CAE workflow, we use real geometry objects, while in CAENexus workflow, we use abstract objects, which helps for automation independent of geometry. Let's understand abstract class more thoroughly and understand how it is topologically equivalent to real geometry. Let's imagine a class fluid. A fluid in computational context will be a three-dimensional closed space separated by boundaries with outside world. Only for understanding purpose, let's represent it as a cube. But in abstract context, fluid can be of any shape and it always be contained by physical space boundaries represented by 2D boundary. Similar to fluid class, we can define various classes like size is used to define mesh sizing, porous is used to define porosity without having to have a real geometry. These classes and their topological entities always be used to define various attributes similar to real geometry. We will see more details in following slides on how this basic idea is used to capture analyst knowledge in a tiny reusable abstract model. So try to imagine that an abstract class fluid, it will have a definite dimension, that is 3D, but no shape. It will also have imaginary closure entities like boundary, interface and interior. Abstract class is an imaginary object, but it do have geometrical interpretations in terms of dimension, its closures and relation with other classes similar to real geometry objects. In order to get a concrete representation of an abstract class, it needs to be combined with real geometry, and the reality depends on geometry the class is combined with. For example, the fluid class can be evaluated to a cube or a pipe depending upon what it represents in CAD geometry. Just to summarize about abstract class, we can define various abstract classes like fluid, solid, size, etc., which can be used to define simulation physics independent of geometry. Abstract classes are entities which have some specific dimensions like 3-dimensional, 2-dimensional, 1-dimensional and 0-dimensional. For example, when I say fluid as my 3D abstract class, then it can be represented by any 3-dimensional entity like cube, cylinder or a HVAC system. That depends on which geometry you use with this abstract class. Similarly, when I say inlet 2D, then it represents two-dimensional entity, and that entity can be anything like inlet of pipe or inlet of a HVAC system or inlet of a tube, or let's say inlet of evaporator, inlet of heater. That depends on which geometry you use with this abstract class. Same applied to 1D classes and 0D classes. So in nutshell, abstract classes are the entities which have some specific dimensions like 3D, 2D, 1D or 0D, but does not have any specific shape. Shape is defined when we use this particular geometry with these abstract classes. We have already seen some details of CA geometry and abstract classes. A quick comparison is shown here. Both CA geometry and abstract classes have specific dimensions like 3-dimensional, 2-dimensional, 1-dimensional and 0-dimensional. But CA geometry have specific shape and abstract classes do not have any specific shapes until we use any specific geometry with the abstract classes. Both have enclosure entities. Both CA geometry and abstract class has closure entities as shown. That is vertices, edges, faces and region. It combines a volume similar to CA geometry. In abstract class, let's say fluid class, its vertices, then its edges, its faces and its region. So until now we understood what is abstract class and how it is used to define CAE objects independent of geometry. Let's now understand some basics of abstract model. So the abstract model is built using 4 basic building blocks. The first one is component. The component represents the geometrical entity of the physical product and is a geometric placeholder in the abstract model. For example, let's say pipe or a condenser or a evaporator or a heater or a bolt. The second building block is a class. As discussed earlier, the class represents geometric entity which has a dimension but no shape. The class can be a volume, surface, curve or point. You can relate the class with CFD physics. For example, a fluid class will represent a three-dimensional fluid space. Classes have dimensional closures which define the boundaries of the class. For example, the boundary of fluid will be a two-dimensional. The closure entities also have a direction representing inside or outside of the abstract class. The classes, when interfaced with other classes, can have a relation in between themselves representing the common entities between them. So this is our third building block, that is relation. For example, here when we add class B, the interface between the two classes represents a separate set of surfaces. Last building block is attribute. The attributes are behaviors that user attach to abstract class or its closure entities. For example, a wall boundary condition can be attached to boundary of fluid. Notice here that the attributes or behaviors are attached to class which represents simulation physics and not to the component which represents geometry. So this is the basic difference in traditional preprocessors and CAENexus, which enables users or analysts to capture the knowledge and automate the workflows. Here is a schematic of a very simple abstract model. Notice here that the component is attached with multiple classes based on its purpose in the simulation. For example, fluid class can be used to define material and boundary condition, while the class size A can be used to define mesh size and curvature refinement. So this property helps the analyst to author reusable abstract model that can be used for different CAD models. Let's now understand the abstract model reality. Like a real geometry contains various volumes, abstract model contains various abstract classes defined as per their physical significance and their relations. The abstract model, when combined with real geometry, will give a concrete representation of CAE simulation model. Thus, the behavior of classes and the relations will be determined by the real geometry it is combined with. For example, in model 1 below, the relation between class A and class B will be evaluated to a common geometric face, while in model 2 it will be none. Let's quickly compare the traditional approach and CAENexus approach. In traditional approach, let's say we have this CAD model 1. So user will manually set up the physics for each part, let's say boundary conditions or cell zone conditions, and he will run the simulation. Suppose there is another CAD, let's say CAD model 2. Here also the user needs to define similar, more or less similar boundary conditions or cell zone conditions with slight change. Then again he has to repeat the process and manually set up the physics for each part and run the simulation. So if there are n number of different CAD parts, then user needs to manually set up the physics for all those CAD models and run the simulations. But in CAENexus approach, so user needs to define boundary conditions and cell zone conditions or the physics solver physics using the abstract classes, and abstract model file will be ready. And if there is another model with similar physics, then user just have to tag that CAD model with the same classes, and the already created abstract model will be reused, and it will save the analyst time. So if there are n number of different CAD models and having same physics, let's say HVAC model, and there are different HVAC systems or different HVAC models available. So if using abstract classes or using abstract model technology, if the physics is set up or this abstract model file is set up, then user just have to tag the CAD model and use the same abstract model file to generate those n number of simulations. Let's have a brief overview of CAE workflow. So CAENexus separates the engineering tasks in two separate roles, as a CAD specialist and a CAE specialist or a analyst. The CAD specialist prepares the CAD model or captures the computational space suitable for CAE. For example, for CFD, it will derive the fluid spaces. Then he adds the string parameters with certain naming conventions to the CAD parts. These string parameters are called as component and class tags in CAENexus context. On the other side, the analyst authors the abstract model by importing the tags in CAENexus from a sample CAD model. The imported classes are now treated as abstract geometric entities. Then the analyst attaches the simulation attributes like mesh size, material, boundary conditions, etc. on the abstract geometric entities. The analyst then creates simulation model, mesh model, and solver input files. He will check and update the abstract model to capture all the requirements by testing it. We call it as authoring mode. Once the completed abstract model is then available throughout the organization for synchronization with the CFD CAD models. This brings us to the production mode in the workflow. Here, user just synchronize the tagged CAE CAD model with the standardized abstract model, and rest of the steps like creating simulation model, mesh model, and export the solver files are all automatic. Here is the quick summary for the complete workflow in 3 simple steps. Combine the CAD model with standardized abstract model to create simulation model. Next, create mesh model and export solver model. So CAD to CFD reliably in 3 simple steps. These steps also can be executed using Python scripts or using suite functionality for multiple model. Let us see how CAENexus handles the drastic geometric modifications by taking two quite different geometries and physics. The first one is simple viaduct model, while another one has a fan inside. So a geometric abstract model shows a different classes like fluid, air, inlet 2D, outlet 2D, air rotate A, to which attributes are attached. When abstract model combined with two different CAD models, it produces two different simulation models. As you might have noticed, the air rotate A isn't applicable in viaduct model, but it is still present in the abstract model. During the synchronization of viaduct model, CAENexus identifies that there is no real component assigned with air rotate A in geometry and eliminates the class along with attribute. This is how CAENexus makes the abstract model reusable. You can then automatically generate mesh and solver files. Then you can take the solver files ready to run on your cluster for actual simulations. So thank you for watching this video. See you in next session.